Hello students, in today's lecture we are going to solve NCERT exercise problems from 14.1 to 14.8 on waves. This is our disclaimer. Learning objective. After this lecture, you can easily solve problems based on key characteristics like amplitude, energy, wavelength, frequency and period using proper reasoning and calculations. This is the index of our today's lecture. We will discussing NCERT exercise problems from chapter of waves. There are total 19 questions in this exercise. We are going to cover 8 questions, that is 14.1 to 14.8. A string of mass 2.50 kg is under a tension of 200 Newton. The length of the stretched string is 20 meter. If the transverse jerk is struck at one end of the string, how long does the disturbance take to reach the other end? Let's see the solution. The given information, mass of the string m equal to 2.50 kg, tension in the string T equal to 200 Newton, length of the string 20.0 meter, mass per unit length, that is mu equal to m divided by L. So we know the value of m and we also know the value of L. So m by L, mass per unit length. So just put the value of mass and L. You will be get the value of mu. So it will be 0.125 kilogram per meter. Now the velocity v of the transverse wave in this string is given by the relation that is v equal to under root T by mu. So just put the value of tension and mu. So it will be under root 200 divided by 0.125. So after dividing 200 by 0.125, we got 1600. Now we will take the square root of it. So it will be v equal to 40 meter per second. Alright. So this is the velocity of the wave in the string. Now time taken by the disturbance to reach the other end T equal to L by V. So just put the value of L and V. So the expression T equal to 20 divided by 40 means that the value of T is the result of dividing 20 by 40. So the time value T equal to 0.50 second represents a duration disturbance take to reach the other end. Now we are going to moving on to the next question. A stone dropped from the top of a tower of height 300 meter splashes into the water of a pond near the base of the tower. When water is the splash here at the top, given that the speed of the sound in air is 340 meter per second and g equal to 9.8 meter per second square. We are to calculate the total time taken for both the stone to fall and the sound to travel back up. Let's start the solution. Let's see what is the given in the problem. Height of the tower, uh, 300 meter. Initial velocity of the stone, u equal to 0. Acceleration, a equal to 9.8 meter per second square. Speed of sound in air, 340 meter per second. Alright. Now, time t1 taken by the stone to strike the water in the pond can be calculated using the second equation of motion, as s is equal to u t1 plus half g t1 square. So, by substituting all the given values, we get the expression 300 equal to 0 plus 1 by 2 into 9.8 into t1 square. So, rearranging the terms to calculate time, so t1 equal to under root 300 into 2 divided by 9.8. So, solving this, you will be get 7.82 second. Alright. Now, the time it takes for a sound to travel to the top of a 300-meter tall tower can be calculated by dividing the height of the tower by the speed of the sound. So, T2 equal to 300 divided by 340. So, after dividing, we get T2 equal to 0.88 second. Therefore, the time after which the plus is here, T equal to T1 plus T2. Alright. So, T equal to 7.82 plus 0.88 represent an addition problem where the variable T is the sum of two decimal numbers. To solve it, simply add 7.82 and 0.88. So, after addition, we get the time T equal to 8.7 seconds. Clear? A steel wire has a length of 12.0 meter and a mass of 2.10 kg. What should be the tension in the wire so that speed of a transverse wave on the wire equals the speed of sound in dry air at 20 degrees Celsius, which is equal to 343 meter per second. Alright. Let's start the solution. Let's see the given information in the question. Length of the steel wire L equal to 12 meter. Mass of the steel wire M equal to 2.10 kilogram. Velocity of the transverse wave V equal to 343 meter per second. Now we have to calculate a mass per unit length. So that is M divided by L. So by substituting the value of M and L, we got mu equal to 2.10 divided by 12. So mu equal to 0.175 kilogram per meter. Clear? Now, for tension T, velocity of the transverse wave can be obtained using the relation. So V equal to under root T divided by mu. So after rearranging, we get T equal to V square mu. Relates tension T in a string or rope to the velocity V of an object moving in a circular path and the mass per unit length mu. So this expression calculates the value of T by first squaring 343, then multiplying the result by 0.175. After calculation, we get the value T equal to 2.06 into 10 raised to the power 4 Newton. Clear? Use the formula V equal to under root gamma P divided by rho to explain why the speed of sound in air A is independent of pressure, B increase with temperature. C increases with humidity. So you have to find out the regions of the three cases. Let's start the solution. Let's see why the speed of sound in air is independent of pressure. So let's take the given relation of velocity v equal to under root gamma p divided by rho, represents the speed of sound in a fluid. Here v is the velocity of sound. We know density rho equal to mass upon volume. So mass is capital M and volume is capital V. M equal to molecular weight of the gas, and V is equal to volume of the gas. Clear? Now equation V equal to under root gamma into P divided by rho reduces to V equal to under root gamma PV divided by M. You know rho equal to M divided by V. For constant T, PV equal to constant. Since both M and gamma are constants, V equal to constant. Hence, at a constant temperature, the speed of sound in a gaseous medium is independent of the change in the pressure of the gas. Now, let's discuss B part of the question, which is why the speed of sound in air increases with temperature. So, consider the given relation of velocity V equal to gamma under root gamma P divided by rho. Consider this equation first. For 1 mole of an ideal gas, the gas equation can be written as PV equal to RT. So P equal to RT divided by V, and consider this as equation second. Alright. Now substituting equation second in equation first, we get V equal to under root gamma RT divided by V into rho. So it will be under root gamma RT divided by M. Consider this as equation third, where M is equal to rho V is a constant. Gamma and R are also constants. We conclude from equation third that V is directly proportional to under root T. Hence, the speed of sound in a gas depends on its temperature. As the temperature of the gas increases, the molecules move faster, allowing sound waves to travel more quickly through the medium. Therefore, the speed of sound is directly proportional to the square root of the absolute temperature. Now, let's discuss C part of the problem, which asks why the speed of sound in air increases with humidity. Take the given relation of the velocity. So V equal to under root gamma P divided by rho. So let Vm and Vd be the speeds of the sound in moist air and dry respectively. Let rho m and rho d be the densities of the air and dry air respectively. Clear? Now, speed of sound in moist air, Vm equal to under root gamma P divided by rho m. Alright. So, speed of sound in dry air is Vd equal to under root gamma P divided by rho d. So, on dividing equation 4 and 5th, we get Vm divided by Vd equal to under root gamma P divided by rho m into rho d divided by gamma p. So after rearranging the terms, Vm divided by Vd equal to under root rho d divided by rho m. Now, when water vapor is present in the air, it replaces some of the heavier air molecules, such as nitrogen and oxygen. This makes the air less dense. The inequality here, rho d is less than rho m, means that the density of dry air, rho d, is less than the density of moist air. So velocity of the mass Vm is greater than Vd, damping force. The speed of sound is faster in moist air is greater than it is in dry air. Thus, in a gaseous medium, the speed of sound increases with humidity. You have learned that a traveling wave in one dimension is represented by a function y equal to f of xt, where x and t must appear in the combination x minus vt or x plus vt. That is y equal to f x plus minus vt. Is the converse true? Examine if the following functions for y can possibly represent a traveling wave. A. X minus vt whole square. B. Log x plus vt divided by x naught. And C. 1 divided by x plus vt. Let's see the solution. The converse of the given statement is not true. The essential requirement for a function to represent a traveling wave is that it should remain finite for all values of x and t. Clear? So, A does not represent a wave. For x equal to 0 and t equal to 0, the function x minus vt whole square becomes 0. This means that the starting point in the space and time, the value of function is 0. Alright. Hence, for x equal to 0 and t equal to 0, the function represents a point and not have a wave. So, let's see second part. B does not represent a wave. At x equal to 0 and t equal to 0, the function represents the initial conditions of a system. This equation shows a situation after substitution where the logarithmic of 0 is being calculated. So log x plus vt divided by x naught is equal to log 0, which is equal to infinity. A traveling wave is a wave that moves through space, carrying energy from one place to another. This function described here does not have a finite value x equal to 0 and t equal to 0, which means it does not settle to a single value at that point. So it's not a traveling wave. Now, part C does not represent a wave. At x equal to 0 and t equal to 0, we are evaluating the function at the origin. So 1 upon x plus vt. So 1 upon x plus vt equal to 1 upon 0 equal to infinity, undefined. A traveling wave must have a finite value at all points in space and time. If a function does not converge to a finite value at x equal to 0 and t equal to 0, it means the wave's amplitude becomes infinite or undefined at that point. This makes the function unsuitable to represent a real traveling wave. So this function does not represent a traveling wave. A bat emits ultrasonic sound of frequency 1000 kHz in air. If the sound meets a water surface, what is the wavelength of A? The reflected sound. B. The transmitted sound. Speed of sound in air is 340 meter per second and in water 1486 meter per second. Let's start with the solution. Let's see the given information in the question. Frequency of ultrasonic sound emitted by the beat f equal to 1000 kilohertz. Speed of sound in air 340 meter per second. Speed of sound in water 1486 meter per second. The wavelength of the reflected sound lambda r is determined by the speed of sound and the frequency of the sound wave. So lambda r equal to v divided by nu. So just put the values, we will get the value of lambda r. So it will be 3.4 into 10 raised to the power minus 4 meter. Now frequency of ultrasonic sound nu equal to 1000 kilohertz. So nu equal to 10 raised to the power 6 hertz. Speed of sound in water Vw equal to 1486 meter per second. So the wavelength of the transmitted sound is given as lambda t is equal to 1486 divided by 10 raised to the power 6. Lambda t equal to 1.49 into 10 raised to the power minus 3 meter. A hospital uses an ultrasonic scanner to locate tumors in a tissue. What is the wavelength of the sound in the tissue in which the speed of sound is 1.7 km per second? The operating frequency of the scanner is 4.2 MHz. Let's see the solution. So let's look into the problem to check what is given. Speed of sound in the tissue V equal to 1.7 km per second. V equal to 1.7 into 10 raised to the power 3 meter per second. Alright, because this is kilo. Kilo means 10 raised to the power 3. So it will be this one. Operating frequency of the scanner nu equal to 4.2 MHz. So it will be 4.2 into 10 raised to the power 6 Hertz. Now the wavelength of the sound in the tissue is given as lambda equal to v divided by nu. Shows the relationship between the wavelength lambda, speed v and frequency nu of a wave. So substituted the given values in the formula. This expression calculates the wavelength lambda by dividing two numbers in scientific notation. The numerator is 1.7 multiplied by 10 to the power of 3, which equals 1700. The denominator is 4.2 multiplied by 10 to the power 6, power of 6. So after the calculation we get the final value of wavelength 4.1 into 10 raised to the minus 4 meter. A transverse harmonic wave on a string is described by y of xt is equal to 3.0 sine 36t plus 0.018 x plus pi by 4, where x and y are in centimeter and t in second. The positive direction of x is from left to right. A. Is this a traveling wave or a stationary wave? If it is a traveling, what are the speed and direction of its propagation? B. What are its amplitude and frequency? C. What is the initial phase at the origin? D. What is the least distance between two successive crests in the wave? Let's see the solution. For part A, yes. The given wave is a traveling wave moving with speed 20 meter per second in the direction right to left. Let's see the explanation. Equation of a progressive wave traveling from right to left is given by the displacement function. So y of xt is equal to a sine omega t plus kx plus phi. Here omega is the angular frequency, k is the wave number, phi is the phase constant. This wave is moving in the negative x direction if the phase is omega t plus kx. Now the given equation is y of xt is equal to 3.0 sine 36 plus 0.018 x plus pi by 4. So on comparing both the equations, we find that equation second represents a traveling wave propagating from right to left. We are writing down the equations first and second together here. So y of xt is equal to a sine omega t plus kx plus phi. Y of xt is equal to 3.0 sine 36t plus 0.018 x plus pi by 4. This is equation second. So after comparing above two equations, we get omega equal to 36 radian per second and k equal to 0.018 per meter. Now we know that nu equal to omega divided by 2 pi and lambda equal to 2 pi by k. Also v equal to nu lambda, so speed of traveling wave v equal to omega divided by 2 pi into 2 pi divided by k. So solving this, you will get omega by k. So v equal to 36 divided by 0.018. Solving for v, so v equal to 2000 centimeter per second, v equal to 20 meter per second. Clear? Hence the speed of the given traveling wave is 20 meter per second. Now amplitude and frequency of given traveling wave are 3 centimeter and 5.73 hertz. After comparing the given wave equation with the general expression of wave, we got amplitude of the given traveling wave is a equal to 3 centimeter. Frequency of the given wave nu equal to omega by 2 pi. Solving for frequency, so nu equal to 36 divided by 2 into 3.14. So nu equal to 5.73 hertz. Initial phase at the origin is pi by 4. Explanation. The initial phase at the origin is found by setting x equal to 0 and t equal to 0 in the wave equation. So y of xt is equal to 3.0 sine 36t plus 0.018 x plus pi by 4. Initial phase on 36 into 0 plus 0.018 into 0 plus pi by 4. Solving this, you will get pi by 4 radian. Since 36 both 36 and 0.018 are multiplied by 0, their contributions are 0. Therefore the initial phase is simply pi by 4. Clear? Now least distance between two successive crests in the wave is 3.49 meter. Let's see the explanation. Least distance between two successive crests Wavelength is the distance between two consecutive wave crust, can be calculated as lambda equal to 2 pi by k. So lambda equal to 2 pi radian divided by 0.018 per centimeter. So solving this, you will get 348.89 centimeter. Now this wavelength can also be expressed as lambda equal to 3.49 meter. So lambda equal to 3.49 meter. Alright. Thank you for your attention. I hope this lesson was helpful.